We hope you, your family, and your loved ones are staying safe and are able to help others in need today. We want to welcome you to our session by offering this universal uh, message of peace. Lokaha samastaha sukhino bhavantu. Om Shanti Shanti Shanti. You all are here to listen to our session to understand how did we grow our data practices to service insights and analytics from over 20 million smart home consumers with over 500 million connected devices over the history of time. Okay. In order to get to our session, we want to first give you a little bit of a backdrop of what does Plume do as a business, what are its business imperatives, and what are some of the problems we are trying to solve, and the relation of our teams in solving our various data teams in solving these problems. I'm going to be able to talk about some things that are public facing and available on the internet. So, but from that, I'll try to derive some internal facing challenges that we are solving today. So Plume is in the business of providing consumer experiences for the connected smart home. We run our products in tens of millions of homes and monitor and manage various types of services in these smart homes. Okay. To give you a sense of some of the things our business teams are looking for, I'll talk about some business teams who are our stakeholders and consumers of our data products. So to begin with, out here, you can see on plume.com, we've offered most recently during our 20 million smart home launch celebration. Marketing people wanted to come and offer some insights from the data that we have so that they can launch campaigns on the public web. So marketing is one of our consumers. They look for things like, what's happening across homes across the world, across different deployments of our customers, and based on insights gained from different types of connected devices. So out here on the left, you can see a heat map showing all of our deployments across the globe, which we have to update on a daily basis. Similarly, we have requests coming from product management, and the product managers want to understand how various features are working, whether people are turning them on or off, how they are performing in the field, etc. And again, that happens over all of our homes across worldwide regions. There is people from our products teams, which are product engineers or algorithms engineers, who are trying to improve and optimize our product performances in the connected smart home. So they look for things like, how is our product optimizations performing? How is the connected device quality of experience? And these kinds of metrics and KPIs, they are looking to see over geographies, over period of time, and over different types of telemetry metrics that we are gathering. The most obvious ones that you're seeing over here are things like traffic patterns over a period of day, internet speed tests and availability over time, across time and across geographies. Okay, so another team that is seriously uses a lot of our data products and insights is our net ops teams. This is the network operations team that is responsible for rolling out features and firmware updates across lots of different regions, across lots of homes. And when they roll out new firmware and they roll out new versions of software, they want to understand that everything is still performing stably, relative and comparative to what they were seeing before that change was introduced. So these are the various types of insights we have to serve for these different types of stakeholders. And the teams that serve these insights span across three types of teams. We have the data engineering team that ingests and processes data by building pipelines. We have the data science team that uses our data to tune and optimize their algorithms and introduce product innovations. And we have the BI and analytics teams that take the data and the tables that we are producing in our data warehouse and that expose it through dashboards, ad hoc reports, and various types of insights that our stakeholders ask of us. Okay, so this is the context of our company and the team structures and the kinds of problems that we are trying to solve. Now, armed with this, we'll move into what's the agenda for the session. We are, so I am Samir Vaidya. I work as an architect in Plume, and I focus on data engineering, BI, and analytics concerns. Later on in the session, my colleague Raghav Karnam is going to join us, and he's an expert in data science and machine learning engineering in the company, and he's going to talk about some things that they're doing with machine learning and share some insights with you from that. Our session today is targeted really at beginners. We've advertised it as a beginner level session. And what we mean by beginner level is somebody who is relatively early in their journey in adoption of these various technologies for building big data analytics. And specifically, if you're interested in looking at DataBricks, data platform, Lakehouse, SQL analytics, those kinds of areas, what we are going to talk about today is how we build our current generation of data processing platform on these technologies and the lessons we learned over this and what the overall environment looks like. We are going to be talking about how we used job clusters to improve our productivity. We use our notebooks for developer productivity, and some areas about metadata management for data processing, for converting the big data that we are processing into SQL queryable data for various applications. And I will be focusing on that. And when Raghav joins us, he will be talking about machine learning lifecycle. Okay. We do hope that those who are new to this area gain from our presentation today. And for those who are more experienced and you feel that you know a lot of this stuff, we also hope, since you have joined our session, we hope you do carry away a few insights and aha moments where you learn something from our session, and it's worth the time you invested in us. Should you like our session and what we have to say and what our company is doing, we would love for you to refer your friends to apply for careers at Plume in data areas. Our journey in big data started from early days, so roughly over 5 years ago. At that point, when we started looking at data processing and analytics, we gravitated toward and selected the Apache Spark framework for all of our data processing. And over a period of time, we've continued to use that and are successful and happy using that. And again, also from early days, we were a big AWS shop. So we've embraced and deployed on AWS across multiple regions in the world, very happy and successful with that platform, with that hosting service. And therefore, from early days when we started our data processing with Spark, we naturally gravitated towards using the existing AWS big data processing frameworks at that time. For processing big data clusters, we used the AWS Elastic MapReduce, which offers us hosted clusters that you can click through and quite easily generate these clusters for your processing. Once we finish processing the data, in order to expose it through our data SQL analytics warehouse, we started using AWS Athena, which takes the underlying data and makes it accessible over SQL. So think of Athena as our data warehouse. And in order to take the underlying big data and expose it through SQL over Athena, you have to use something called AWS glue crawlers. I can almost never say glue crawler correctly, but I think this time I got it right. The glue crawlers take underlying file system, whether it's Avro, Parquet, or JSON or CSV, and generate metadata out of it auto-magically to expose them as SQL databases and tables, and you can configure it to do this. So this was our initial infrastructure that we got started out, and in early days, it was working reasonably well. When the team sizes were small, the amount of data we were processing was reasonable. What started happening is over a period of time, as the data evolved, we started getting more and more data. The number of developers increased. We started getting more and more teams building these jobs. and we were having slight difficulty keeping everything consistent and standardized. What started happening, we started running into some bottlenecks, and I want to kind of talk about those as some of the challenges we were facing and how we overcame them. So we'll start with talking about the Spark data processing clusters. What we found at that time, and this was, roughly 2 years ago, is what I'm describing at this point in time. So these challenges were being faced 2 years ago, and then I'll explain kind of how we overcame them. So at that point in time, for the Spark data processing, what we found that we were processing data both in development and production. And in production, our DevOps team liked to control the resources and manage the resources for us. And what we found is that as people started using the EMR clusters in production operations, and we started writing more and more jobs, we found it complicated to figure out how to size the EMR clusters, how to configure them, and how to scale them and use them in a just-in-time manner for just the jobs that we were processing. It turns out that we at that point had not quite figured out how to automate this, and I don't know if this is possible today or not, but at least at that point, we had an infrastructure where we would create a cluster and just leave it running because it was too complicated for us to terminate it, shut it down, and then again reconfigure it and relaunch it. So because of this complexity, we got into this habit where the EMR clusters were just built once and left running. And once we left them running, then as we started adding more and more jobs, it became complicated for us to figure out how to size them, how to grow them and shrink them. And we weren't quite able to figure that out. For the clusters that were running in production, we found that for some of our batch processing, which ran infrequently or just occasionally over the day, we were just running clusters all day long and essentially considerably reducing the resource utilization of those clusters and unnecessary paying for resources that we were not using. So this was what was happening in production. In development, as developers wanted to create their own clusters, we went through a period of time where we let developers do their own clusters for a while. And that, that flexibility bounced back on us because in some cases, what the developers did was they left the running clusters, large running clusters over long weekends and things like that, and realized that, they were not being super responsible. And the reason for that is there was not an easy way to build a cluster and automatically time it out and come back to work and start it up and so on. So because of this lack of automation, we found that the developers were not able to use them very responsibly. And so we went through a period of time where we tried to create clusters and manage the sharing of clusters. And that got quite complicated because of the logistics of using shared libraries on the clusters and so on. So these are some of the challenges we were having with clusters. At that point, also in terms of the development processes, what we found was that most developers were using Spark submit jobs and either SSHing into the cluster and running things on Spark shell, or just running jobs and looking at log files to do their debugging and troubleshooting. And overall, we found that the developer experience and productivity was rather low. There was probably one or two resourceful, brave engineers who figured out how to use notebooks, but it wasn't a widely adopted practice. So for some reason, we were living in these dark cave ages as far as the developer experience goes. So these were some of the challenges we were having with Spark processing. For actually taking the underlying processed data and exposing it, what we found was that the glue crawlers, sorry, my bad. I want to go back to AWS Athena. I want to talk about challenges we were having with Athena. So with Athena, we were mostly happy. It was performing quite well for almost all the queries that we were trying to do. There were a couple areas that were the gotchas for us. One of the areas, while most of the queries worked pretty well, we found that in certain occasions, when our data scientists were trying to look for deep insights by running complex queries over large data sets, gathered over large periods of time, they found that they wanted to run complex SQL, and they found that they would run it for several hours, and then eventually it would just time out or run out of resources, and they were not able to actually finish those queries. So, and the the thing we found kind of as a blocker for us is that there didn't seem to be any real solution to this. So out here you can see that this is the kind of thing that you get if you run out of time or if you try to use resources that they're not willing to do, not willing to give you. And this is because Athena is a serverless environment, and serverless has pros and cons. The pro is that you don't have to mess with the capacity planning and managing the resources and all that. That's what makes it appealing and attractive. The downside is, should there be a time where you have a complex, large query you want to run and you're willing to pay for it because it's valuable enough for you that you don't mind using the extra resources, spinning them up and paying for it, there is really no such option. You're just out of luck over there. And so in that case, the concept of serverless works against you because you don't have the control to spin up additional resources that you need for the processing you need to do. So that was one thing that we didn't quite like about it. Another area that we had an issue was that some of the data that was available, we found a way to expose it to our support agents, and they found it quite useful to take this data and surface it into the support web applications. And they would use it for serving customer support calls and so on. And we thought, hey, this was great. Like we can expose this Athena data over these web applications. And it worked well for a while until the support volume started increasing. Then as the volume started increasing, what we found out was that Athena gives you a fixed number of queues for fixed number of queries. And if one day too many support agents were working on the app, suddenly the queues would get filled up and no other processing could work. Everybody else is now blocked because all the queues are taken up by the support agents. So we then realized that, oh, this is kind of not good because it's a shared queue across everybody who's using this across the account. And that's not quite going to work. So that idea of not having control over pooling the resource and deciding which consumer of the applications gets how much of which resource, that facility was not available. So in this case, we started feeling constricted, constrained by the serverless concept. And the last area was related to the metadata management, the glue crawling. Is while I said that most of the times as a developer built these underlying pipelines, they found it quite easy to configure these crawlers, point them at a location, and it would automatically build metadata. This evolved organically over a period of time and worked well for a while till it stopped working very well. Okay, and what we noticed was that our schemas had started evolving over time. And as the schemas evolved, the versions of the schemas evolved. And also, as we changed some processing technology, we found that certain files in the underlying file system were getting introduced differently than they were before as we changed our technologies. And what we noticed is that if the developers were not careful configuring the crawlers with just the right exclude clauses and the right parameters, the crawlers would go berserk and start generating a lot of corrupt or incorrect metadata that was not useful. So this is an example of the kind of thing that can happen um, uh, based on some underlying situation. So the crawler suddenly starts generating large number of data tables because it thinks that the underlying partitions or files are data tables because it's auto magically trying to detect what the tables are. And in this case, if you're not very careful or if there's a certain situation you don't account for, quite easily you can make a mess out of it. Okay, and so we found that this idea of a automatic metadata management system based on crawling was not a very good situation. So these were some of the things we were struggling with. And so that's when we decided to look for a better solution. And we came across DataBricks, and DataBricks first demonstrated us this concept of clusters, and we absolutely loved it because in the clusters they showed us that you can create these standard clustered or shared clustered between developers, and it's quite easy to create it and provision it. And then for your jobs, you create something called job clusters. And the job clusters simply spin up when you submit a job. And when the job is done, they tear down and that's it. You pay exactly for the processing you do with your jobs. There is no idle time, underutilized resources. Also, the standard clusters that we started giving our developers, or we could give our developers based on their technology, they have this concept of build the cluster, and then when it idles out, it just tears out and shuts down. You stop paying for the underlying compute costs. And when the developer is ready to work with it again, they can just click a button and restart that cluster. Or in some cases, you can just submit a query to it and it automatically starts up the cluster. So we found that to be quite appealing, and we decided to embrace that. Similarly, with this metadata management, we quite liked the concept of the Delta Lake. And the Delta Lake is a self manifest management system, which means there is no external additional crawlers that you need to look at the underlying file system and determine what the table structure looks like and what the schema looks like. Okay, the Delta system writes the data and the metadata as it updates the data. So the writes and updates are heavy, but the reads are speedy, quick, and efficient. And there is a way to optimize the underlying data. So we found that to be more appealing than having to build a manifest, the automated metadata management system based on crawlers. So these were some of the appealing things for us to get started with Databricks. And over the next few slides, we're gonna talk you through our journey of how we transitioned to the Databricks platform. What were some of the challenges we solved to scale it up across our worldwide processing? And what are some of the benefits we gained out of that? So let's start with topic number one, which is talking about the operational productivity and developer productivity. And for that, we had to deploy Databricks workspaces all over the world in various regions of our processing, and then let the developers use them in every area of processing. So I'm going to talk about how we went about that and what were some of the challenges that we had to overcome over there, and what are some of the best practices we gained out of that. Okay. Now realize that Databricks is a installed product, which means that it's not like AWS native where you can just click some AWS service and enable it and turn it on. You have to actually plan for a Databricks installation, which is called a workspace. And in our case, because we were operating in multiple regions in multiple AWS VPCs across the world, we had to plan for n number of workspaces. Right now, we are roughly under 10 of these, but we had to plan for these. And in each case, we had to plan for dual pairs, which is the idea of a dev workspace and a production workspace in each of the regions. So in order to plan for that, we realized that some of the things we have to be careful with is, number one, we have to standardize the namespaces. What do I mean by namespaces? Any given Databricks workspace has a URL that you use to access and refer to it. So we then worked out that the best practice for naming should be consistently used everywhere, because if you get it wrong, unfortunately, there's no simple rename command. You have to literally tear down the whole thing and rebuild it. So after one such expensive lesson, we learned our lesson in standardizing the namespaces. And today we follow a pattern, which is something like company name dash environment name dash region name. And then after that, you get the .cloud.databricks.com. So we standardized that namespace for all the workspaces as we started installing them. While planning for the workspaces, we also realized that we should plan for bucket names. Again, it's one of those things where you have to standardize on the bucket names, because once you pick the bucket during the installation, you cannot change that bucket name. And it's best for the automation and DevOps and all those practices to have the consistent bucket names everywhere. So we learned that we should standardize the namespaces while creating these workspaces. The users and groups. So in AWS, within our account across various VPCs, we could just create groups and users once, and the same one is available through AWS IAM worldwide. But with Databricks, that's not true, because each workspace has its own concept of users and groups. But so which means that we had to manage the users and groups in each of these workspaces. So imagine like times 9 or 10 of those, right? But the good news is that they offer something called SAML single sign-on. It's called SCIM integration. And with that, what you can do is you can use our SSO. So we use our single sign-on SAML identity provider, and we map our users and groups in the SAML SSO that our IT maintains. So anytime new users or new employees join the company, as part of the onboarding process, IT provisions them into our single sign-on provider, and then the underlying integration automatically pushes the users and groups into the Databricks workspaces. And that allows us to do user management across these large number of workspaces. So that's how we solve that problem. And then within each of these, you have various resources like clusters, jobs, databases, etc. So for that, we realized quickly that we need to automate the role-based access control for that and apply it consistently to every workspace. So we had to build some scripts to take all of these underlying resource administration roles and automate those for applying them across all of these workspaces. So these are some of the things you have to be aware of and plan for. One thing we realized is also that over a period of time across these various regions and workspaces, the Databricks themselves are upgrading their underlying services. And over different periods of time, these can go through maintenance and upgrade periods. And we found that I want to give a shout out to the status.databricks.com, which we found to be quite useful to understand when something doesn't look quite right and we're trying to wonder if it's our issue or their issue. You can look at status.databricks.com, and that tells you what's happening in various workspaces and regions across the world. So this was how we set up our various workspaces across the world. Now, once we set up these workspaces, we wanted the developers to start using it. And what we noticed is that almost from day one, everybody quickly gravitated towards using notebooks as their integrated developer experience, as their IDE of choice. And I'm proud to announce, like after a year, we took a survey, and a number of developers claimed in the survey that they felt subjectively that they felt their productivity was up 30 to 50% by using and adopting the notebooks. So for the notebooks, the cool thing is that the notebook has things called cells. And in the cells, you can write in your language of choice. And so we have our data engineers who use Scala. So what they do with Scala now is they develop their underlying job and create jar files out of that. They upload it to the cluster, and then they're able to interact with it for development and testing and just see how well their job is working. They're able to interact with it through the notebook, through the Scala code. Our data scientists are able to write Python-based code and then use the Python code to interact with their underlying algorithms and so on against the data. And our SQL analysts are able to use SQL, and they use the SQL cells to interact and play with the data and do their development process with the notebooks. So that all is working pretty well. And one of the interesting things we were able to do is previously our analysts would rely on the data engineers to convert anything into a scheduled job. But with the notebooks now, what they're able to do is they're able to write some code in SQL and click a button and just schedule it as a scheduled job. So it's quite easy. So you can just write your code and your logic for the job, and then schedule it, and Databricks will run it on whatever schedule you specify over there. So they were able to do quite a quick and easy job of getting something and rolling it out as a job without waiting for data engineering team to do it for them. Over a period of time, we learned a couple of things. One is that the notebooks in early days were not having underlying Git support, but recently they introduced GitHub repository support, and we are quite happy with that. The GitHub repository allows us to map the notebooks to underlying repository and manage the versioning of that in the underlying repository. So certainly you should look at GitHub repos. And then in terms of scheduling, we learned that although the scheduled jobs are quite nice and convenient, that we were not hooked up into our Airflow-based job monitoring system. So over a period of time, we converted those over into Airflow to get the monitoring. So we stopped using the Databricks scheduler and simply scheduling those jobs using Airflow to get the job dependencies and the monitoring. So we started using Airflow for that. Another thing you can do is, if this is not adequate, there are a couple of other alternate experiences that we are using for developers. So one is that you can configure using Simba drivers, you can configure a SQL IDE. So you can actually connect to Databricks clusters using your commercial SQL IDE that you might like better. Or you can use your developer IDE like IntelliJ or PyCharm or something like that. and submit your code into the clusters for Spark using a technology called DataBricks Connect. And our developers are using a combination of all of these technologies to improve their productivity for development. We'll talk about clusters now. And for clusters, I mentioned early on about job clusters and high concurrency and standard clusters. So with job clusters, what we are doing is we are submitting jobs from our Airflow jobs, and each developer who is responsible for the job gets to decide how much resources their job needs. And they're writing the Airflow DAGs to create the job sizing, the cluster sizing, and submit that job into the cluster. And then Databricks will spin up a cluster as you specify, run your job and tear it down, as I mentioned. Okay. So in this, what we've done is we use their concept of cluster policies so that we can keep some amount of limit and sanity check so that somebody doesn't go too crazy with it without us finding out about it. Okay. So we are using the job cluster policies for that. We played with standard and high concurrency clusters, and because of the different points in time where developers are working and not enough concurrency, we concluded that the standard clusters were better for us. And the high concurrency cluster is a lot more expensive to run, but it's built in such a way that it balances all the incoming requests. So if you have a number of developers working simultaneously, you should use the high concurrency clusters. But if you have sporadic use, sparse usage of the clusters, you simply give them the dedicated clusters. And over that, we uncovered some best practices from that. One of them is that for the clusters, we initially tried to use spot instances everywhere. We got excited that these instances can be quite cheap, and we should use spot instances. And then what we learned over time is that that's a bad idea, because what can happen is sometimes a job will run for 3-4 hours, 5 hours, and then it will terminate because the Spark driver node just goes away because of the underlying spot instance being taken away, and now your entire job fails. So what we learned is that we should use reserved instances for the driver nodes and spot instances for everything else, and that has been working pretty well for us. Uh, Another issue we uncovered was that when developers submit these jobs, they have to submit the jobs under their own credentials. And once you do that, no other developer can go and troubleshoot your job. So if your job failed and one of your teammate wants to help out using this job or troubleshooting this job, that was not being possible. And then Databricks introduced this thing called service principles. And the service principle concept allows you to take essentially like the equivalent of a service user that is headless. And you can create that in your group and use the service principle for launching your jobs. And once you do that, then the people in your group are able to actually see the logs and do the troubleshooting and so on. So we uncovered that we should learn service principles for managing jobs. One thing we learned is that this idea of subnets, I should have probably mentioned it in my earlier slide about planning the workspaces, but this was a lesson we learned after the fact. At one point, we were having some issues with our some processing, and we uncovered that while installing the workspace, our DevOps team had installed it in an existing VPC with some other services, whereas Databricks best practices recommend that you have a dedicated subnet with adequate subnet space. And we learned that lesson the hard way. We had to tear it down and rebuild the workspace in an appropriate dedicated subnet. So do remember to give it a dedicated subnet and give adequate room for us to grow. Because again, this was something we learned that in the beginning, we thought, how many instances can we use, right? But as our processing grew, we suddenly started realizing that we can use quite a few instances, and that we should probably plan for a large enough subnet that we're not worried about running out of space. So this is something you should plan for, to build a large enough dedicated subnet for your underlying clusters and workspaces. For high availability, I mentioned that we use Airflow for our job scheduling. And what we learned over a period of time is that Databricks services and APIs go through a maintenance period. And what that means, maintenance period, is that for some period of time, your job might invoke the API to launch the cluster and run your job, but that invocation fails because the API is undergoing maintenance upgrade. Now, they are kind enough to announce it in the status channel and the alerts and all email alerts and those kinds of things. But never the same, you have to account for it in your job launching and execution. So what we learned to do over a period of time is to retry the jobs, because when these APIs go away, then they do come back in 15, 20 minutes. And then we learned that instead of just letting it fail and dealing with it manually, we've built the logic into our Airflow jobs now to relaunch the job within a few minutes and try it for like up to 30 minutes. And now that has been working pretty well for us. Another thing we learned is that in some situations, as the number of instances starts growing and our data processing increased, we learned that there are situations where AWS underlying availability zone in a certain region runs out of certain types of instances. And when that happens, there is nothing you can do. On one occasion, we complained to DataBricks support, but then they said, look, we rely on the underlying AWS to give us instances. And if they don't have that instance type, there's nothing we can do, which we thought was reasonable. And so then what we learned to do is to retry the jobs in such a way that you can ask it to run in a different availability zone. And then that's working much better for us, where now if the underlying availability zone is out of instances, we simply try another availability zone and get our job executed in that availability zone. So you should plan for such retry logic to try in different availability zones, should a original one run out of instance types. Another thing we experienced, and this is very much real, they talk about this in their documentation, something called idempotency of jobs. So remember the example I gave you where the API submission used to fail. So in this case, what happens is we found some situations where our retry logic would resubmit the job and the same job would run 2 or 3 times. And this actually created quite a few problems for us, because in some cases, it would write multiple files underneath and it would mess up our logic, which relied on counts of the underlying records and things like that. So it actually gives you bad data outcomes, and we had to figure out how to deal with it and fix it. So then we learned about this thing called idempotency tokens. So now when we submit our job, we submit it using the idempotency tokens. And that is now made every job completely unique in time and space. And we no longer suffer this problem when we retry the job of having multiple submissions on the job. So highly recommend using idempotency tokens for your job submissions. So these were some of the lessons we learned for operating the clusters. And this has allowed us to pretty much for the developers to do most of this in a self-service manner and considerably reducing the involvement and overhead of DevOps for managing and maintaining these clusters. Now, as people started using these clusters, at some point we had to renew our licenses and figure out like what our spend was. And up until that point, I'm a bit embarrassed to admit had not been doing a very good job of tracking our spend. But now we've learned our lesson. And what we learned was they have these wonderful usage reports where you can use AWS tags. And as long as you tag it correctly, you can actually slice and dice your spend in quite a few ways. And so what we learned to do over time is to apply tags for the different ways we wanted to see our spend. So by the cost center, by what kinds of projects we were spending these clusters for, which team was using it, which individual owner was responsible for something, and which environment and which region the processing was running. And by creating these kinds of AWS tags for launching the clusters, we are now able to go and look at the usage reports and slice and dice them. The usage reports are available directly through the Databricks account management console, or they can also allow you to export the data and build your own custom reports. So we started doing that to export the custom reports and then do our own reporting for usage based on Tableau. So this is very useful. So I highly recommend you plan for this right from inception. All right, so we talked about establishing the clusters and establishing the developer experience. I want to talk about shift gears and move into the metadata management and how we are managing query performance and how we move from Parquet and SQL to the Delta Lake. So we talked earlier on about glue crawlers, and I'd mentioned that glue metadata system keeps the MetaStore updated. And a MetaStore is essentially a definition of tables and how they map to the underlying file system. Okay. Now, when you move to Databricks, we kind of tried this idea of hybrid idea to say, maybe we can leverage and reuse the existing AWS glue system, etc. But that actually turned out to be quite complicated and wasn't giving us a clean separation between these concerns. And so after struggling with that for a while, we decided to just create a clean slate and completely separate what we were doing with AWS Glue and Athena from what we were doing with DataBricks. So we decided to completely embrace the DataBricks MetaStore for managing metadata for DataBricks. And in that now, uh, uh, we wanted to start out by using our existing Avro and Parquet files and simply using that to map the metadata into the DataBricks MetaStore. And we uncovered that that was actually a little complicated, because what that requires you to do is it requires you to write your own equivalent of crawlers. Because now remember that, while I complained about glue crawlers, the good news was they were at least there to automate the thing for you. But if you want to do your own Parquet and Avro using Databricks, then you have to really work out your own effective metadata management system. And we did some of that because we wanted to shift over into Databricks and then slowly migrate over into Delta. And I'm going to talk about what the Delta migration experience was. But what we uncovered by using Parquet and Avro through Databricks SQL queries is that that really doesn't work as efficiently and optimally as the original the Athena system does, which is based on a different technology than Spark SQL. So based on those experiences, we basically decided to move to Delta Lake as quickly as possible, because Delta Lake arranges the underlying data in a more optimized manner. And that works much better with Databricks. So if you're planning to migrate from legacy Parquet and Parquet and Avro into Databricks, then really practically speaking, you should immediately plan for migrating to Delta Lake, because the legacy underlying Avro Parquet support, while exists, is not very good. The SQL query performance and all is not very good over there. And you have to maintain your own metadata, writing your own crawler system. So I would avoid doing that if I had the opportunity. So we had to go through that system and create crawlers, but I would avoid doing it. Now, what we have to the rescue is Databricks has this technology called autoloader, and our resident solution architect helped us configure the autoloader, and it worked quite well. And with the autoloader, what you can do is you can just write a few lines of streaming code and point it at a source. And essentially in the streaming code, you can convert it into and write it as Delta and keep it up to date. So it becomes like your ingestion system to ingest into the Delta system. Okay, so that is something I would recommend you give a try. But I want to spend a little bit of time on how we went about migrating our existing Parquet to Delta, because I think that's kind of a challenge we had to undergo. And some of you who have existing legacy data and trying to do this are going to have to do the same. So out here, the first thing is that you have to uncover where your Parquet and Avro data is being used, and which means you have to have quite a clean in-house catalog and data lineage understanding of what is the data, where is the data, who is using it, and where is it coming from, right? And for this, you have to have all the underlying metadata. What I mean by metadata is the DDL. For each of these data, you have to have the definition language for each table and how it maps to the underlying data. So we started by cataloging all of our paths and all of our schema DDL for these underlying data. And so once we did that, we started planning for how to convert the underlying Parquet into Delta. Now realize one thing, that there is a quick and easy command for converting Parquet to Delta, because essentially Delta is just Parquet plus plus, like, you just write some metadata on top of Parquet. So that is quite an easy, convenient command. But if you had Avro, there is no such easy command. For Avro, you actually have to do some job ingestion to convert the Avro into the Delta. Okay, but luckily for us, a lot of our underlying data was Parquet, so we were able to do this a little easier. So for this, what we did is we had to first plan for which are the consuming pipelines. Okay, now realize this, that the first step in this is what I call a big birthing bang, where you have to take all the underlying data and you have to convert it from Parquet to Delta. And then once you do that, that solves the problem for the initial data that got converted. But imagine this, on the very next day or the very next hour, some job is going to run and is going to write more data, right? So then you don't want a situation where the job is writing Parquet data into the underlying data that you converted to Delta. So then what we had to do is we had to figure out which all jobs we had reading and writing the underlying Parquet data. And we had to modify these jobs very surgically to convert our read from Parquet write to Parquet to read from Delta write to Delta as appropriate. Okay, so we had to take all of these pipelines and convert all of this code and have this ready. In some cases, we also found that there were external consumers of our underlying data who were directly loading the data instead of using SQL. They were directly loading the data from the underlying file systems. And we had to coordinate with them to say, hey, we are converting this into Delta, and you guys should be ready. And when the time comes to shift over along with us to this Delta system. So after we did that, we then created scripts to automate and convert all of this data. We paused all of our pipelines, converted all of the data, then started the pipelines with the new code, which was reading and writing as Delta. Okay, then resume all the pipelines, and next day onward, all of this code is now reading and writing Delta format. And this is kind of how we did our conversion from Parquet to Delta. And in order to maintain a backward compatibility with Athena, there is a way to take the Delta data and expose it through the manifest system and make it available to Athena. Now, for that, we had to also create our own MSCK repair mechanisms to let Athena see that the underlying Delta data is updated. So you cannot use the existing glue crawlers anymore. You have to build your own mechanism to take the underlying data and refresh Athena's metadata system periodically to let it see the updated Delta data changes. So this was our path to conversion from Parquet to Delta. And so at the end of it, we now had effective developer productivity, and the underlying data was converted to Delta and giving us automated metadata management and also better performance because of the underlying Delta system having knobs for optimizing and consolidating files and so on. So based on this, we are now able to use SQL analytics, which exposes this underlying data through SQL. And for that, we simply took the existing usage of Athena and started shifting them one application, one user at a time. Now that our DataBricks MetaStore was implemented and populated, we were able to start shifting these underlying applications from using Athena to using DataBricks SQL Analytics. And for the SQL Analytics, we started by doing a SQL endpoint, which we call general purpose, and started onboarding most of the applications to it. And only over a period of time, when somebody had a specific need for doing more, we started creating further custom endpoints and clusters. Also note that in the SQL Analytics product, if you're not very excited about the SQL bot that they offer, we are able to use an external SQL ID like dbeaver. And also SQL Analytics is able to serve web APIs, the thing I was complaining about running out of resources. And we are now able to use SQL Analytics endpoints by scaling up the underlying clusters to meet API performance. So this is the end of my story. I talked about how we overcame a number of issues with workspace management, clusters, and notebooks, how we upgraded to the metadata and embrace SQL Analytics. I hope you found some of these insights useful. I want to transition and hand this over now to my colleague Raghav, and he's going to talk about what he's doing with ML in the company. Over to you, Raghav.
Good morning and hello to everyone. I'm myself Raghav and I lead the machine learning and data science team at Plume. I'm here to speak about the machine learning lifecycle within Plume and how we have taken the help from DataBricks to automate a lot of things. So Plume on business front focuses on a lot of machine learning use cases. The primary one, the first and the primary one we started with was ability to cater Wi-Fi to all the homes in a seamless way. Okay, to give the Wi-Fi in a best possible, give a best experience of Wi-Fi, we need to understand what kind of a devices which are there in your home and what kind of a movements you have in your home. Like for example, you live most of the times in your living room, we have to adjust our Wi-Fi to your living room. And if you have most of the times, a TV which is a 5 gigahertz, we have to adjust the Wi-Fi accordingly. To do these things, we need to understand both the nature of the devices which are in your home, the kind of a devices in your home, the kind of a movements you have in your home. This is one very big space where the machine learning has helped us. The second area was once you have this Wi-Fi, what do you want to do with this Wi-Fi? You want to do a lot of things, but you want to be safe. You want to be, you want to be protected while you're going on internet. So that's where our second use case comes up, cybersecurity, where we try to digitally protect our customers from external attacks. That's a cybersecurity area, and we do lots of machine learning in that space. Then, like the topic indicates, we are in 20 million plus homes with 500 million plus devices. That's a lot of data coming in. And how we can help our consumers. Plume is in consumer home services business. Like I said, Wi-Fi is our first service. The second is a cybersecurity. The third is preventive and proactive maintenance. Is there a way we can know that you're having a glitch in your Wi-Fi experience and fix it even before you realize it? That's a huge area of interest for us because we want the Wi-Fi experience to be the best for you. That's another area. Then came another use case where like how we can we were protecting you digitally. Can we do a physical protection for you? For example, today when you're away from your home, let's say you're using Ring or any other product, like you have a sensors on your door, etc. And when you say home away, if some intruder comes in, you get a pop-up saying that, hey, there's some intruder, right? But here you need an external sensor. Can we do this without using external sensors with your existing Wi-Fi access points? That was a challenge we wanted to do. And how do we do that? Is another area of a machine learning focus. Can we sense the motion detection using Wi-Fi signals? Yes, the answer is yes. We have solved it to some extent. Yeah. And within the motion, there's a lot of challenges. Like you're away from your home, but your pet is moving in your home. You should not be calling it as an intruder. So there's a lot of nitty-gritties where we have worked and improved ourselves. And then there's a lot of innovation areas within Plume where we're working. We can probably not discuss, but there's a lot of machine learning happening within Plume. So these are the machine learning areas of focus for us. And there's a huge expectation from machine learning teams because we have to be very fast, adapt to the needs of the market, at the same time, adapt to the scale at which we are growing. Now let's go back to our day one. What are the challenges we faced in our first generation of ML lifecycle and ML ops, how we ended up with DataBricks, okay? Basically, our evolution started with a single focused question. Initially, when we started doing that, started doing data science and machine learning, we were a very small team with enthusiastic engineers who wanted to do a lot of cool products which will go to the market faster. And we did it like everyone. We had a single machine learning engineer and data scientist responsible for doing various stages of life cycle. But at some point of time, you want to increase the rate at which the features go to the production, okay? And that's when we started to thinking, what are the various stages and how we can optimize each and every stage. For example, this is a very standard process or steps involved in machine learning. You curate the data, you do feature engineering, you do a lot of things. How do you do that? The data engineers are supposed to curate the data in a raw format. Then building of the model is generally a data scientist's responsibility. So within that, how do you tune performance and tune your metrics, keep some thresholds? Deployment models, we generally have ML engineers doing that. How do you do that when existing production model is there and you add additional model in an A/B testing mode? How can you do it seamlessly? Then the last step is when you're integrating the models, you're interacting with a lot of software engineers who are building microservices. How fast you can integrate with these other teams and how well they can understand the machine learning models you give them so that they can define simple pass or fail. That's another phase. The last phase is about operating the model in production. How do you see the model drift or data drift, etc. Okay, so this is the areas of concern we had. And like Samir was pointing in the initial slides, the data scientists used to own a lot of these things. And we wanted to break down both in terms of process, in terms of people, in terms of technology tools, and optimize these things. The people part, you can see we have clearly defined our journey. This is the people path and the teams part. Okay. Whereas the tools and technologies, the data scientist was initially we were, small team, and a couple of us were smart enough to host the notebooks for the entire team, and we were going, but it was not taking us too long. Then to track the ML experiments, like, performance metrics, we had an ML flow, open source ML flow on a specific server where we're tracking experiments. But the infrastructure burden was on top of the data scientist side. So how do we address this? How do we free up the space and the burden on the data scientist? That was the one question we asked. So that was the first question which led us to a discovery of DataBricks, where the DataBricks offers an IDE called DataBricks Notebooks. These notebooks help us to spin up and spin down the clusters, Spark clusters. Previously, in the previous world, data scientists used to spin up the EMR cluster and host notebooks himself, ML flow clusters himself. So that's where we picked up DataBricks, because it helps us to spin the clusters up and down. And the data scientist doesn't need to worry. And the IDE notebooks, they're always hosted by DataBricks, so we don't need to worry about it. These were the cool factors which took us in. That was the first reason we got into the DataBricks. And then we slowly used it for, it's a model performance metrics, ML flow, and model registry. ML flow for both tracking the performance metrics and model registry. Okay, so I'll walk you through with a demo. And I've tried to balance this entire demo and everything in such a way that it caters to the interest of both the beginners and the people who are already using it. And I've taken the liberty of using some open source data for this case of a demo. Okay. And general architecture within the Plume with ML flow. This is an offline architecture, not a real-time one. This is how it looks like. We have various Databricks workspaces. We have Databricks workspace for, in general combination, we have 10 plus Databricks workspaces. We have a general combo of development Databricks workspace and a production workspace. Okay, the way the development workspace and the production workspace interact is through a common repository. That's where we store our models. Okay, and this is how the general architecture looks like. Most of the times, our engineers, our data scientists and ML engineers are pulling the data from the S3 or Mongo or some other third-party data sources. They're doing the feature engineering on top of the Spark cluster, and they have their own ML framework. And we use Horovite for the deep learning framework. And we use ML flow for tracking our experiments, and then ML flow repository for, for registering the models. And the registered models are used by the production Databricks workspace. This is a general architecture which we have done. Okay, and one of the good things we have found about is like for example, in case of Plume, we have multiple workspaces. We have a workspace for EMEA, Databricks workspace for EMEA, Databricks workspace for US, Databricks workspace for Asia Pacific. Okay, and within that, each and every region, for example, EMEA has its own development instance and development workspace, and it has its own staging workspace, it has its production workspace. So what we do is all our development happens in something called as a development space, where we do build our models, and then we push it to the staging through a common shared model repository. So we have reserved one workspace as in a shared model registry or workspace. That's where we check in our models. And once the models are registered, they can be accessed by a different workspace. It can be in a different region also. Like, we can have a centralized workspace in one particular region, and the workspace in a different region can access the models. So that's what we have set up. And in the coming slides, I would like to demo a few of these things so that it becomes much more clear rather than being in an architectural slide. I would like to show you guys something which we have done within a small example. In this demo, what we want to show is like how ML flow can be used to train, log, and track the machine learning models. For this case, I've used a deep learning model. It demonstrates using LSTM autoencoder. But more important is we want to show you how ML flow helps us. Okay. So with an ML flow, you can always set an experiment to whatever name you would like to. In my case, I'm just giving some random name over here. And you can always watch the experiments by clicking over here. So that's how you create and set your experiment. Then you can start your experiment with a particular run name. In this example, I've just given a latest run time as such, but you can do your custom naming convention for starting your run. Once you do that, you can do the rest of the steps are very regular. Like, you get your train data, you load them up. Then the most important step within each and every machine learning step, is like, what are the parameters you want to log? For example, when using your ML experiment, if you observe here, like these are the two experiments which I have done in the past. If you click on this experiment, you see a lot of parameters which are very necessary for your model tracking. Then there are metrics like loss or the number of anomalies or any custom metrics which you guys are defining. So these are the metrics. So each experiment will have these parameters and metrics. So based on your needs, your machine learning algorithm, you will pick up these parameters and metrics. Few of them can be constant parameters, few of them can be metrics, which will vary with each and every run. Then it also has artifacts. If you can observe these artifacts, it has an ML model, conda, YML file, and everything. So, but going back, right? If you go back to the previous slide, just a second. So once you create your experiment, you run your experiment with that particular name, and you have to define these parameters and configuration metrics. Like in my case, slice calls is nothing but each and every business segment. Imagine your model is going to impact various segments or various countries, various segments of products or various segments of countries. You want to slice and dice and improve your monitor your model performance on those slices. So it's very important to have the slices. You might be having specific metrics in your mind. You might have some time steps, seasonality based ones involved. So whatever it is, you have to set those ML flow log parameters. And this is how you set your log params. Once you set your log parameters, you can follow the general process of pre-processing, building your deep learning model. I'm going a little fast here because these are regular steps. I've used a tuner, which is a Keras-based tuner. You can use any tuner for your hypermodal parameter tuning. Okay. Then the last thing which I wanted to explain is like, this is how you are logging your parameters, where you're fixing the batch size and everything. And then this is my architecture where I have LSTM layer and dropout, etc. Use your own architecture. Once you train your model, okay, and you log your metrics, okay, what you're supposed to do is you're supposed to register your model. That's what I wanted to cover. This is all training the model. One of the most important thing which I found is like, how do you wrap your pre-processing, the feature engineering and the model together so that you can create in a Python class which can be leveraged by inference engines. So they have a very beautiful thing called MLflow PyFunk model, where you can add your custom pre-processing as well as model together so that can be leveraged. So that's what we are doing here. We have a custom pre-processing data processing module and ability to leverage your model. So you also can set your environment variables and you can set your labels. Okay. Once you do it, you log your PyFunk model, and then now we can move and register the model to a remote repository. I'll just show you how do you register the model to a remote repository. Like, you want to find out your best experiment, in your case, your loss function or whatever you're choosing, right? In my case, I'm just setting this experiment. I'm going to use this code to pick up the best experiment based on the loss. Okay. And I order by loss, I get the best experiment. Then using the registry.ur, this is what I wanted to share you. Like in the slides I was showing, we have multiple workspaces and have one workspace which has a common registry. So in our case, for the case of this demo, I've picked up a particular registry URI where you can set your registry URI, and then you can push, register your model to that particular run of your model to that particular registry. Okay. This is a little tricky, the registry URI, and this workspace will have access to the common workspace using keys. Okay, that's nothing but a scope and this set of 3 keys. Once they are configured, you can access the common repository. This is how you register your model. Once you register your model, I just want to show you the registered models, how they look like. An example of registered models is like, let it pop up. Let's say once it's registered, so you can see various versions of it, each and every version, how it's performing and everything. So this is the version 3 of it, everything. So for the sake of demo, I didn't yet pull up the runs and everything, but that's how your registered models look like. How does your inference look like? The inference looks like this. Just give me a second. And you have your inference model. So using your Python model, you can invoke your data. And this is very important because your registry URI is the one which you have to carry across your workspaces. Based on the registry URIs, you pick the latest version of the model, or in my case, I'm taking the model version 2. You can automate this, and you take a particular model name and particular version and load that model here. And then you can run your inference on top of it, and voila, you get the results. I think this is where I want to conclude. In this case, these are all the regular trends, and the red dots are nothing but the anomalies or outliers in the performance. So hope you guys got some glimpse. I had tried to give you an overview of how you use MLflow for logging your metrics and registering your models and running your inference. Thank you, everyone. Have a nice day.